So shall we go on? So now what we want to do, we want to just see how value network if we want to do TRPO and PPO. So yeah, we can do exactly the same thing as we have done before, only we just add the value network there, right? So you can use one separate network to be your value network. You can incorporate the value network inside your policy network. You have a shared architecture. This is also possible. And then you use your policy to sample the environment, a batch of trajectories. Then you get those trajectories or that batch to somehow update your value and policy network together, putting some mini batch, a stochastic gradient descent, right? So now let's start with TRPO, and then we're going to get into the other one as well. So this guy was the TRPO algorithm that we had. We discussed it last time. So what we do here, we are going to sample trajectories, and then maybe we do multiple epochs. So we talked about this, that we are going to sample, we got our policy network, we use that to sample a complete batch, and then we go over it for multiple epochs. And every time that we go over one trajectory or a mini batch, we are going to compute the advantages. If we want to do it now, we have already the value network, right? So we are going to use that value network to sample the advantage. And we can compute, using those advantages, we can compute the gradient, right? So you have the gradient, then you can do whatever we used to do in TRPO, meaning that we're going to estimate the Hessian. Out of that estimate, we're going to use gradient conjugate gradient, to find out this vector y, and we use vector y to just update your parameter. We check if we are just deviating the region condition, then we back the line until we get into the trash region, right? And by doing that, we have updated our policy network, right? This is what we have done before. And then in this algorithm, we basically have this value network just added, right? And the only thing that you should do extra here is that you also compute the gradient of your value network, right? So like in line 7, you use policy gradient theorem to compute this gradient, right? And then you can also compute this gradient using the same advantages as before, right? You get the gradient, you backpropagate over your value network, you get the sample gradient of your value network. Now, once you're over with everything, then you update your policy network and also you update your value network with the same SGD that you had before, right? Everybody's cool, yes? So this is a kind of higher level version of the active critic here, but there is one key point that you should pay attention here, especially when you do it in practice by sampling a batch of trajectories and using it for training. So the key point here is that when you are computing the gradient of the value network as well as the policy network, you need to use also importance sampling to make sure that the advantages that you are computing are actually averaged over the target distribution, not the sampling distribution. So if you remember last time when we talked about that, I told you that you are going to get something like this, right? And then this guy was the one. So let me check if I am. Sorry, I just feel that I'm lost. Oh, no. So I don't know why I have this here, right? Because, yeah, this is the indicate. Oh, sorry. This is the indicate of my policy networks. It's not the value network yet, right? So here what I'm speaking is just, I try to recall you, but I guess probably what I touted, like it was already a couple of sessions past. But here, well, this we have done before, right? So you remember when we did TRPO or PPO, we always update or gradient using this term, right? And I told you that this term is actually the gradient of the importance sampling version, right? The policy that you have as the target divided by the policy that you have sampled with. The key point here that I want to indicate is that you should also do the same thing when you are doing value estimation. So what does that mean? Say that I have my old policy network, pi theta old, right? And I got this policy network, and with that one I just sample the whole full batch of samples. And I want to use that guy in order to update my value and policy networks. Now the thing that I do, after every update, I am getting a new policy, right? So when I update my policy network, my parameters of the policy network are changing. This means that I am supposed to focus on estimating the value of this policy, right? But if I want to use the same samples that I sampled initially and I put inside my batch, then I am just getting samples of the old policy, right? So the thing that I should do, I should pay attention. I should keep the importance sampling term also there in order to convert whatever I have inside my data set into the samples of the new updated policy, right? So what does that mean? That means that if you want to update your value network, you are going to focus on the value network, which is estimating the policy, values of your policy pi theta, right? And that guy is the expectation of whatever you have. This is the, for example, TD expression, right? Expected over the policy that you are playing with, right? So you are taking one sample of this one as an estimator, but supposedly this is an estimator of this guy, right? But if you have already one mini batch, which you have one batch of samples that you have already sampled with your previous policy before update, right? So those guys that you have are not samples of this pi theta, right? They are samples of pi theta old, correct? And then because of that, if you simply use them directly to update your value network, you are simply updating the value network to estimate the values of your previous policy, right? Not the current policy. So what's the trick here? Basically, you just use importance sampling also on the values, right? To just make sure that you are converting those samples into the new samples, right? So how can I do that? I could say that, well, I want to estimate this expectation, the expectation on the new policy, but I have the samples of the old policy, right? So if I want to do importance sampling, I have the same guy as before, but I'm going to multiply it with the ratio of the densities, right? So every time that you update your policy, you have a new policy network, right? You get that policy network, you divide it by the density that you had when you just sampled your batch, right? This is the importance sampling argument, and you multiply it to your samples all the time, right? Everybody's clear? So you use this guy. So the sample that you are going to use is going to be this one when you want to update your value network, right? So if you do basic TD, you don't have this fraction anymore. This is a sample that you have, right? But this is a sample of old policy, right? And when you train your value network by this sample, this simply means that you are training your value network to predict values of your old policy. But you don't want that, right? Because you want to use this value network to compute the advantage of your current policy, and you update with that one. So you need to have this importance sampling argument as well. Everybody's clear? OK. So yeah. So this is going to be the way that you are computing the advantage. So the advantage is going to be whatever sample you have times the importance sampling argument minus the value that you have at that particular stage, right? And this importance sampling argument is just needed to make sure that you are not losing the track of your updated policy, right? Now, sometimes people simply write it down in this form. But this is not completely correct because, I mean, you cannot say that this guy is exactly this multiply with this ratio, right? There's no action really involved here, right? So you need to actually sample with the marginal distribution of the states, that D guy, you remember? but that is too complicated to do, right? This is why people do this approximation. So basically, they get the advantage which they have out of the samples inside the batch, right? And then they multiply the whole thing with the ratio. It's roughly okay, right? It's not 100% accurate, but it's going to work, right? And as engineers, as well, as long as it's working, it's fine, right? So it's a nice approximation, but you cannot really say that this is very accurate approximation, because the ratio, like importance sampling argument for the second term, is a bit hard to write analytically, right? Because it depends on the state at time t, which you have started with some random state, and you played randomly with your policy, and the policy was actually changing as well, right? That's like a super complicated thing to compute, right? So you can simply just ignore it. Yeah. So that is the way that people, that is the way that you need to just to transform the advantages inside your old batch into the advantages into the new batch or new updated policy, right? And then when you are updating your value and policy network, you need to work with this guy, not the previous guy. Not the green U, but this one, right? And green U is simply this guy. You can always convert it, right? Questions? No question? Okay. So yeah, this is the correct way of estimating the advantage. And if you don't do that, this is one point. If you don't do that, and you are doing small batches, and you are just doing few epochs on one batch, throw them away, and then you update, you don't see a very sensible difference. Like sometimes that one, without having the importance sampling argument, it also converges, right? But if you increase the number of epochs that you are going over, because your policy network starts to somehow get into a kind of a steady state, like getting out of the previous region and getting into a new region, then you're going to see the difference. It's going to be obvious in that case. Or if you are going to work with larger batches, like you would say, I do not have time to just sample every second epoch, so I'm going to just take a large batch, just train over it enough number of times, and then I go for the next batch of trajectories, then usually you see a very significant difference, right? Now, this is the correct way of doing it. All right. Some baseline implementation, they do not have it. If I remember correctly, the one which is given by OpenAI, it has it, right? But if you don't see it, it does not mean that you don't need it. You simply just forget to do that. Right? This is one of the tricks some people just ignore when they are implementing. Okay, so yeah, now how does this guy reflect if you're just updating your value and policy network? Well, for the policy network, I think we discussed it last time. This is the same thing for the value network. So if you want to update your value network, you're going to use those sample advantages as the sample of the error terms that you need to update your gradient with or compute the gradient with. And then this guy, you should simply replace it with this this importance sampling argument, right? Everybody's cool, right? Questions? So that's about the value gradients. And then if you want to update the policy, you should definitely do the same thing. As I said, we did it last time. What we can do it once again, just to make everything clear. So if you are updating your policy, well, you are using policy gradient method. So the policy gradient theorem, sorry, this means that the gradient is going to be the average of the log likelihood, right? Gradients of the log likelihood. And this is the gradient of the log likelihood. And the thing that you have here is your advantage, right? Now, the thing that I should do, I should replace that green U with the importance sampling argument. This means that I should do this one, right? But now here, because you are computing the gradient of the log likelihood, this is going to simplify. The denominator, pi theta, is going to cancel with the denominator here, right? And then you're going to end up with only this one, right? So it's okay that you use the old advantage that you had. The only thing that you need to know is that how you should normalize your gradient of the policy, right? You should do it with a guy which you use for sampling, not the one which you have right now, right? That's not a big deal. Everybody's clear? Questions? Now, again, this one, if I'm not 100% sure, but if I am not mistaken, I have seen some baselines, like very well-known baselines, that are not doing this, right? And it's not doing very sophisticated impact. But if you want to be 100% precise, this is something that you should consider. Okay? Now, this guy is consistent with importance sampling. If you just simply get this U-old, the old advantage, you put it like, I have seen some people doing it like this. They have the old advantage, so the first line, instead of the green advantage, they just use the blue advantage, and then they keep it here pi theta. Usually, because you are not getting out of the trust region, this is not going to impact significantly, but it's not correct. Mathematically, it's not correct. Yeah, that's the only thing I can say. So practically, depends on the thing you're using this approach for. Okay, so this guy is now the TRPO, the actor-critic version, including all of those, importance sampling, everything. So when you have a trajectory, you can compute the old advantages, right? Because you have your trajectory sampled by your old advantage, right? And now, by your old policy. And you get that one, you compute your old advantage term, and then you use that one to update your both value network and policy network. But the key point is that you should always keep in mind that you should do the importance sampling as well, right? So you get this advantage, you just convert it into the green one, the new one, using importance sampling argument. Now you are going to estimate the gradients that you need. And after that, you just do the basic TRPO, okay? And now, once you have done this, you update your policy network, you also update your value network, and that's it, right? Okay? Now, you typically do this for a bunch of trajectories, right? So you go over one batch for a couple of epochs. Once you are over, then you update your policy, right? This is what I told you last time as well. So this is the classical way of implementing. You get you get your policy, you just collect the whole batch of samples, you go over it for multiple epochs, right? Every single mini batch, you just take a mini batch from what you already have inside your buffer, right? As long as you are doing importance sampling, no problem is going to happen, right? But once you're over with it, like say for 10, 20 epochs, then you just throw everything away, you update your policy for sampling, and you sample again, right? Everybody's clear? Oh, one thing, why I have written here pi theta old to pi theta? So it should be the other way around, right? Yeah, sorry. Don't do that, right? Of course. you gotta get back to the original point. Sorry, the line 11, it's a typo, right? And as you can guess, I tried to just inspect this one because the original version you could not read it, full of typo, and then like everybody was asking, what is that? Oh, one typo, one typo. But I inspected it so many times, but still I missed this one, right? Okay. Yeah. Now you can do also the same thing with PPO, right? So for PPO, you can again do. Now, where does this value network show up? Again, same thing when you want to just compute your surrogate function, right? For your surrogate function, you need advantage, right? And for that advantage, you need to know the value, so you can use your value network to estimate those advantages, right? And once you do that, then you just put it here, just do importance sampling, that's it, right? And you do everything as before, nothing changes. The only difference here is that when you want to just compute your advantage terms, use your policy network. You also use the same advantages to just compute the gradient of your policy network, gradient of your value network, and then you just update. right? Everybody's clear? So that guy, this guy, was the restricted surrogate function that we had. We talked about this, that this is somehow implementing the sort of clipping on our surrogate or on our, say, estimated advantage. So if it is getting too much above 1, then it's going to restrict it to 1 plus epsilon. If it's going too much below 1, then it's just restricting the ratio to 1 minus epsilon. And then by doing that, we make sure that we're not getting out of the trust region, right? If we want to do that, basically we need to compute this advantage term, right? And then you can simply replace that advantage using your value network. And something that you should keep in mind always, that you should keep importance sampling argument here as well, right? So that green U that you see is actually the blue U times the importance sampling argument, right? But in this case, if you write down the importance sampling, it's going to be pi theta divided by pi theta all times pi x divided by pi theta. So those pi thetas going to cancel out, right? Everybody's cool, right? Questions? So that second guy, the green advantage, right? This is the same thing, right? The only reason that I did not put it here, I didn't want to just, make it a giant expression. But that one, that green U, is exactly the same thing we had before. Is this guy, right? Where is it? Right, this one, right? This U, the blue U times, the blue U times the ratio of the policies, right? That's the same thing, right? So your green U, the current advantage is always the old one which you have inside your data set times that one, right? The importance sampling argument. So that's the only thing that you need to keep in mind. So you have your advantage times the importance sampling as your estimator, and then you just compute your surrogate function in this form, and then you just perform PPO as well on this guy, right? Sample a batch, you get your old advantage, and after doing that, you compute the gradient of your value network using the importance sampling, and also you can compute the gradient of your surrogate function directly by applying gradient on this guy, right? And in this one, the only thing that is differentiable is this pi x denominator, right? This is a surrogate function. So you compute this guy. This is the update of your policy network. You compute this guy. This is update of the value network, and you keep on going like this, right? Now, I want to press the next button. Now, do you think that I have still a typo in the left one, line 10 or not? Let's see. Yes! I still have the typo, right? Yeah, because this guy never triggered the signal inside my brain, right? That weight inside my brain was somehow lost. Okay. Yes. Okay, questions? Everybody's going? Yes, go ahead. Sure. Here.
So in PPO, we assume that when advantage is greater than 0, the fraction is also greater than 1. Right?
This ratio, it's not necessarily greater than 1. It depends on the action that you're doing, right?
When the advantage is greater than 0, then that is also greater than 1.
Oh, when the advantage is greater than 0, then this guy is going to be greater than 1, right? It's going to be smaller than 1, I guess. That was the case. If advantage is positive, then this is going to be greater than 1, intuitively. Yes?
So my question is, since we are estimating our advantage, and in the beginning, our estimator of the advantage is not very accurate,
Correct.
Will that cause any trouble?
Yeah, I mean, definitely for the first couple of rounds, like tens of epochs, nothing is going to happen.
So it's possible that in the first couple of epochs, we're not in the trusted regions?
Oh, in that sense, yeah, sure, definitely. I mean, the trust region only makes sense when you have some level of convergence, right? When you have not converged, you don't care, right? Yeah, that's totally correct. So once you have your policy network somehow capturing something, then you start to see that behavior that I told you. Because it somehow needs to be that really your policy understand that this action is giving me a positive advantage, so it means that I should do that action, right? But to be able to understand, it should first capture that pattern from the data, right? Which takes some time, right? But for the initial ones, like, it's never going to do anything, right? So it's a quite long process till it starts to converge, really. Questions? No question? Okay, if you got no question, then yeah, let me just give you this last part. So this last part is about distributed actor critic. So what is distributed actor critic? Well, when you are doing actor critic, you have this option also to somehow have multiple actors, right? And these actors are basically, for example, in the most simple form, they are actually the same policy network, but they are somehow sampling different parts of your environment, right? Then they can do it in parallel, right? So you have the same policy network at one part of the environment, say your environment is a giant space, right? One copy of your policy network is just sampling here, right? The other one is sampling here, the other one is sampling here, and so on, right? So you're going to have multiple copies of your policy network, and every single of them is one actor just acting in one part of the environment. Now, what they can do, they can sample a bunch of trajectories there, and then they can compute the gradient at that point, right? They can share this gradient and all of those trajectories with one server, right? That server, what it does, it can actually just get those gradients to update the policy network, right? So you could say like, those gradients are sample gradients of different regions inside the environment, right? And now if I average all of them, now it's a better estimator, right? So this is what it can do. It can also take all of those, trajectories you got all over your environment, right? And then it can just use them to update the value network as well, right? That is, again, more efficient because your samples are better distributed over the environment as compared to one actor playing in one particular region, right? And in that case, then you're going to have much better samples, much more reliable updates of the value network and the policy network. And the thing that the server, the global neural network, is going to do after some rounds of update is going to somehow give that policy network to every actor, right? It says whatever you have, just throw it away, copy this one, right? Because this is the good policy now, and keep on playing with this one, right? So this is the way that you do usually distributed actor critic. Now, you could have different versions of it. You could have asynchronous and synchronous. Synchronous is exactly the one I told you, right? So you just agree that, yeah, just sample, update, give me something. I'm going to update, and then I'm going to give you back my updated parameters. You just copy, keep on going, right? This is one thing that you can do. So yeah, this is basically the distributed version, and then yeah, the server is going to use the same samples, but samples are collected from different places. And now you can do asynchronous, that everybody is just using the same model every time that they are sampling, and they wait for the server or the global model to just update them, and then they are going on with the sampling. You can also implement it asynchronous, right? And asynchronous could be more efficient in applications where you have different connections, or you have you give different sort of importance to different regions, right? So this might be more efficient, but there is no trick there happening. The only thing is that I can say everybody just go ahead and update your policy by your own, right? And I don't care about that. Just give me your samples, right? And I'm going to update. At some point, I'm going to give you something back, right? and they are going to just give me samples which are not all of them sample with the same distribution, right? But as long as they are not getting totally out of the trust region, then I can trust on those samples as well, right? So you can do asynchronous as well, and the key difference here is that the connections or the communication that you're going to do with the local actors, this is not going to be like on a certain rounds every time they're going to update. So you just give them information once upon a time, right? Or you might even decide to just do it like this guy is getting updates more frequently, the other guy is just getting less frequently, right? You can do that as well. Not a very big deal. So now, yeah, A3C is asynchronous advantage and yes, actor critic, right? So if you do the same thing that I showed you before, actor critic with baseline, but you do it asynchronous, that is A3C. Yeah, and you can find lots of other names, right? A, multiple of them, C, right? And they are all doing the same thing, right? So, yeah, a few points here. So, yeah, I think it's just about the asynchronous. When you are doing asynchronous, it could be a bit harder to converge. That makes sense because you're not actually giving updated policy every single time to everybody. But usually when we are just trying to reduce the computation load, we are more focused on the synchronous versions because they are not different from the original centralized one. The only difference is that you're just doing a distributed computation, which gives you more parallel processing. But as I told you, in practice, if you have something like sensors which are collecting samples for you, then it makes sense to have asynchronous as well. Now, we are pretty much over with this part of this chapter, okay? And you might wonder that if you are free to go and you're going to get rid of me, I am only going to talk about deterministic policy gradient next session, okay? Because I cannot make it in 15 minutes, and I don't want to keep you too much for telling for the beginning story. But the point here is that, yeah, I can make it. I guess I can do the conclusion also next time. So if you're okay on Friday, we just do it a bit, you know, more fast forward, and then I finish everything on that day. So just to give you the idea what we're going to talk, what we have here in this part of the course, this just simple modification we did. That PPO, that TRPO is going to work on most applications that you have. So that is a kind of solid algorithm, perfect, you can use it. The point here is, though, that sometimes in some applications, you find it better that you don't work with a policy network as a random distribution which you sample policy from, but rather you would like to have a deterministic policy. Like you don't care that the policy could be potentially random. You want to just say that whenever I see a state, I do know exactly what action I want to do. Now, what kind of application this makes sense? For example, when you have a continuous action space and you are really looking for rewards which are coming at the preciseness of your action, right? If I have one object, right, and I want to just take it, right, then this arm has a continuous space of action, right? And then if you do PPO, what does it mean? It means that in every single state that it is, right, it's going to randomly decide where to go, right? Correct? Now, the point is that when you start here, it can't just go anywhere, right? But gradually, as you get closer and closer to the target, it's going to narrow down its probability, right? The probability that I move now like this is very high. The probability that I do anything else is going to be smaller and smaller, right? And then gradually, I'm going to take this one, right? But this means that if you really deploy it in practice, you're going to see something like this, right? Because it's still when I am here, there's a tiny bit of chance I just move around, right? Now, what you do, you typically first train it, and then when you want to use PPO or deploy it in practice, you would say, okay, every time, do not sample from the distribution, just look at the action which has maximum density, right? And take that guy, right? This is going to kill this one, right? This is going to make it like this, right? Now, what you can do, you could just, from very beginning, you would say, okay, if I am going to do it at the end of the day, why don't I start training the guy to just do deterministic, right? So at every single point, do not sample from the distribution, just do the action which has the highest probability, right? And then I throw away all the probability thing, so this last part which is computing the probability, and I directly compute the action, right? This is what we call it deterministic policy method, which is a policy method basically. But the key point is that your policy is always indicator, right? That action, right? Now, if you do that, you can basically do the same thing as before, but you don't really need to go the way that we have gone in the policy gradient method. Actually, you can simply use Q-learning. And why? If you remember what we did at the end of chapter 4, I told you if we have a continuous action space, and I have one, say, Gini network, which is able to look at my state and tell me what is the optimal action, then I can still do Q-learning, right? So I'm going to complete that idea for you next time. This is not going to be very complicated because it's basically Q-learning with that extra policy, deterministic policy. But for some application in robotics, people use it, right? And as I told you, the benefit is that, I mean, it's not going to be maybe as good as PPO or those algorithms which are really using a policy network. But the key point here is that it's going to help you with getting away from, possible actions which you don't want to happen, but they have tiny bit of chance, right? If you're doing a surgery, you don't want to have like even a tiny bit of chance that you just put the needle wrong way, right? You don't want that, so this is how you can think of it. So we're going to discuss it, the first part on Friday, and then last part is going to simply be a wrap-up of everything we had. Questions?